All right, for lesson 3, we're going to look at a couple different types of graphs here. For the first part, as we're looking at something called piecewise or hybrid functions, it's simply normal graphs that you've always graphed, but they're going to be limited in their domain. And so for cases like this, we're going to graph like we always would, but we have to take into account what the domain is for each graph. So for these guys, I like to start the graph in pencil. And you'll see why here in just a minute. But if we were to take the graph of just y equals -2, and we were to graph that, we would get a graph that looks like this. So this right here is the graph for y equals -2. It's just a horizontal line through -2 on the y-axis. But we have to now take into account that this graph does not go left and right forever. I can only limit it to the x's that are less than or equal to 1. And so here's where x is 1, and so I have to limit it to where x's are less than or equal to that number right there. And so it cannot continue to go on to the right. It's only headed off to the left. So now that I kind of have that one established, let me darken it just a little bit. So for that one, this is all we would graph for that one there because of the limitation given here by the domain. For the next part, if we said x plus 1, again, you would graph this as here's your y-intercept at +1. Our slope is 1, so it starts at 1, and it goes up 1 over 1. And so we're getting this look right here for the graph. And typically, we would have drawn a line through those points that looks something like this, right? And we would have had that graph, but now we have to consider what is the domain that I have to limit this graph to. And this says I can only use the x's that are greater than 1. So I can only go from here to the right because it says x is greater than 1. And you'll notice that on this one, it doesn't say or equal to. It just says greater than 1, which means we're not including 1. So to show that, we're going to leave it as an open circle. Keep something in mind. When it says greater than 1, that doesn't mean you start at 2, right? Because greater than 1 is barely greater than 1, like 1.000001, right? Is kind of where this graph begins and then goes off to the right forever. So that's why we get the open circle to show that we're not including 1. It's just everything that's greater than that. And so that's our piecewise function for that. Let me give that guy a different color. So if you're ever, and these are kind of good to do in color, if you're ever looking back at your notes, you can kind of identify which graph was which if you need to kind of look back and see what you did on that. So moving on down, it's going to look at another piecewise function right here. So again, in this one, typically if we were to graph x squared plus 1, that means I have a parabola. Its vertex has been shifted up to +1. Right, and you get this like U-shaped looking graph right here. And so typically you would have these values, something like this, and you get this look for the graph. And so that would be the typical parabola. But again, let's consider the limitation by the domain that we see here. As far as this one goes, it says only x is greater than 1. So here's where I get the x's that are 1, and it says it's only greater than that, which means I can only go to the right. So everything to the left of that point needs to not be seen. And again, there's no equal sign on that, so I'm going to put the open circle, and it only goes to the right from there. And so that's the first graph. So that one's good to go. So let me put that one in blue. And so there's my parabola only for the x's that are greater than 1. And so that's the first one. And now for the second one, -x plus 4. Again, this is just a line, so it starts at +4. 1, 2, 3, 4. My slope is -1 over 1, so if I go down 1 over 1, and we have our line that we would typically graph for that one. But again, let's take into account the domain. This one says I can only look at the x's that are less than or equal to 1. So this graph only goes to the left from 1. So we would have to cut it off right there. And you'll notice this one does carry the equal sign, so we do leave it filled in. And so let me see if I can kind of get that one in red. For the sake of your notes, I would kind of do that. That way if you're ever looking back, you can see what you did for each one separately and which one was which. And so those are the two graphs. One thing that you got to notice about this, in all the examples, and this is always going to be true, these will be connected. Where one ends, the other one begins. So notice this one's greater than 1, this one is less than or equal to 1, so this one goes to the right and this one goes to the left, but they're both connected at the same x value. And that's going to be the case, so keep that in mind. Your graphs won't overlap. They both are lined up where x is 1. One goes to the left, one goes to the right, and that's it. That you're always going to get that look. If your graphs ever overlap, then we did something wrong, and so you got to keep that in mind as you're looking at these. Moving on down, we're going to do the same idea with this, but these are now absolute value graphs, and so I just want to remind you of what absolute value graphs look like. So the typical parent function graph, this is your parent function for absolute values, has a vertex at 0, 0, and the easy way to remember the absolute value graph is that it looks like a V shape. So it's going to go kind of a 1/1 slope to the right and a -1/1 slope to the left. And so you get that perfect looking V shape that looks like that. That's the parent function. But let's see how this would affect the parent function. And there's always a couple ways you could do this. You can do it in the calculator, which I'll show you in a second. You could make a table of values. The easiest way is to just use a translation. And if you remember your translation rules, this tells me I'm going to shift 4 units to the right, and this tells me I'm going to shift 2 units down. And so if I took that whole graph and went 4 units to the right and 2 units down, then I can get my graph doing that. So that's an easy way just by using those translation rules. Your calculator can do absolute value graphs, so let me show you that one real quick. You probably haven't used this feature before, but if you go into your y equals graph, so the absolute value sign is if you go under math, and if you bump to the right 1 column, it's the first option that says ABS. So hit enter, and it brings up the absolute values for you. So now I can put in my x minus 4, and I'm going to hit to the right so that I can get out of the bars to throw in my minus 2. And so there's the graph, and if I hit graph, you'll see that I'm getting the same one. Let me do it this way. Same one on the screen that we did right here by hand. Right? You can see it was shifted to the right 4 and down 2, just like we expected. And so that's another way of being able to look at a graph like that. So one more right here. So if I was going to do a graph for this guy, again, we'll build our grid. This one here is a little harder to deal with when it comes to a translation because of the extra number thrown in right here. So whenever they attach a number to x, it's harder to see how that translation would work. And so you might want to take advantage of your graphing display calculator for something like this. The last one was easy because it was just x. There was no number in front of x. But when you throw a number in front of x, that does make it harder to deal with in terms of translations. And so let me go into my graph on that one. And so we're going to do the absolute value. Again, I'm going to hit math and go to the right and just hit enter. If you have, that's not what I want. If you have one of the older calculators and it doesn't bring up the absolute value brackets like this one is, it might bring up parentheses. It still will operate the same way, it just will be showing you parentheses instead of the brackets. But you should still get the same result. But I'm going to do my 3 minus 2x right there for my graph. And so when I go ahead and hit graph on that, here's what we have. So for this one, you might just want, just for accuracy's sake, I would go to the table and plot a few points that way, I can see that my vertex is in between 1 and 2. And so that's something I'll still do by hand. But I can go to my table, and I have unlimited points that I could plot on my graph. And so I'll just do a few that are here in the middle as far as plotting those points. And so let me finish it off with that look right there. And so again, I could tell that my vertex was between 1 and 2, so it should be about 1.5. One way to figure that out is if you set this equal to 0 and solve for x, you'll get 1.5, which is where the vertex goes. So that's another way of figuring that out. But from here, again, I would just plug in a few points. So such as 0, 3. We could plug in the point 1, 1. Let's go to the right a little bit. I got 2, 1. And 3, 3. And so there's just a few points that I could choose to create my graph. So if you're unable to use the translation rules, then take advantage of your calculator and the table values that it offers. That's another good way of doing those.